The last decades of the 19th century marked the dawn of modern physics. It was the period when a new era of science emerged. Scientists discovered the world of atoms that gave a new dimension to further discoveries. Physics attained new heights and scope. 100 years ago, a French physicist, Henri Becquerel, discovered radioactivity that laid the foundation of nuclear physics, and today it is a boon for mankind in the treatment of serious diseases like cancer. Nuclear research has led to the process of identifying diseases and producing new medicines. The story of discovery of radioactivity is actually connected with the discovery of X-rays. It was in November 1895 when, while working on cathode rays, a German physicist, Wilhelm Röntgen, discovered X-rays. A report on Röntgen's discovery was presented in the weekly meeting of the Science Academy in Paris on the 20th of January 1896. In this meeting, French physicist Henri Becquerel was also present. Images of X-rays showcased there fascinated Becquerel, and he became curious to know more about those mysterious rays. Becquerel had already worked on luminous substances. Luminescent substances are of two types. One is fluorescent and the other phosphorescent. Fluorescence is an optical phenomenon in which the substance absorbs the rays in the ultraviolet range and re-emits light in the visible range with a longer wavelength, like fluorescent tubes used in our homes. The tube is lined with a coating of a fluorescent material. When ultraviolet rays are emitted in the tube, the coating of fluorescent material absorbs the UV rays and the tube re-emits fluorescent visible light. Some materials have an afterglow, that is, they appear to glow even after the light source is removed. Certain watches have dials that glow in the dark. Then, there are some glow toys for kids that exhibit this phenomenon. Becquerel had a ready source of these luminescent substances to pursue his own investigations on X-rays. Becquerel hypothesized that a material had to be fluorescent and phosphorescent to emit X-rays. To test his hypothesis, he experimented with uranium salt. He wrapped the photographic plate with black paper, placed a crystal of uranium on it, and exposed it to sunlight. After developing the plates, Becquerel found a black image of the size of uranium on the photographic plates. Becquerel thought that the crystal had absorbed the sun's rays, which was then emitted as X-rays. On the 26th of February 1896, Becquerel thought of doing this experiment again, but for many days the skies on Paris were overcast and there was no sunlight. So he kept the photographic plate wrapped with black paper and uranium crystal in the drawer of his table. At last, on the 1st of March, he thought of developing the photographic plates. He expected a faint image on the plates, but to his surprise, the image was clear and strong. Now how could this be? Uranium was still emitting radiation without an external source of energy. This was something unbelievable. He was confused. It was for the first time that a material could produce energy without being exposed to any source of energy. Becquerel thought, was he observing a long-lasting phosphorescence or maybe something else? This led him to a new path in his investigations. He melted uranium nitrate into a liquid state and then recrystallized it, which seized the phenomenon of luminescence in it. But still, the images on the photographic plate were as strong. The results surprised him, one after the other. Seeing this, Becquerel inferred that the uranium salts were exhibiting a special property. They were emitting a new kind of radiation. Whether the salts of uranium were kept under the sun or in the dark, whether they were phosphorescent or not, they emitted rays in every case. Becquerel called those radiations uranium rays. Unknowingly, what Becquerel had discovered was radioactivity. During that period, Marie Curie was seeking a subject for her research. Curie started her research on the invisible rays of Becquerel. But Curie neither had a laboratory nor the equipment for the research. So, she transformed the godown of a university into a laboratory and started her experiments on the particles of uranium. In order to measure the electric charge of the radiations of uranium, an electrometer made by her husband Pierre Curie was used for the purpose. The machine was not too sophisticated. Pierre and his brother designed it about 15 years prior to this. Marie decided to explore other elements that could emanate radiation. She discovered that thorium also emitted such rays. And then she called this emission of invisible radiation as radioactivity, which is known by this name till today. Marie proceeded further in her investigations. She was exploring such elements other than uranium and thorium that were capable of exhibiting radioactivity. She selected the ore of pitchblende for her investigations. She separated uranium and thorium from the ore and tested the remains of the ore. The results were surprising. She inferred that the remains of the ore were significantly more radioactive than the pure material. In July 1898, she announced that the ore contained some unknown radioactive elements that were present less in quantity, but they were very powerful. After that, Pierre and Marie both began to discover the new substances in the ore. They discovered two new elements. One was named polonium and the other was radium. Radium was thus discovered but was not yet extracted. At last, on December 1898, after a struggle of 4 years, purified parts of pitchblende exhibited glowing particles. They discovered some chemical properties of radium. The whole scientific world bowed their heads in the honor of Pierre and Marie. For the discovery of radioactivity, Becquerel was awarded the Nobel Prize for Physics in 1903, which he shared with Pierre Curie and Marie Curie. Madam Curie was the first woman to receive the glorious Nobel Prize. In 1911, Marie Curie was again awarded the Nobel Prize in Chemistry for discovering polonium and radium. Curie then became the first person to get the Nobel Prize for both physics and chemistry. In the history of the Nobel Prize, Marie is associated with many glorious achievements. She is the first lady whose daughter was also awarded the Nobel Prize. Scientists considered the discovery of radioactivity a miracle that unfolded many surprising facts. Radium and other radioactive materials that were discovered had another interesting property. As they emitted energy, they got converted to these elements. Before that, scientists used to believe that the elements always exist in their original forms. Actually, all the elements are made up of atoms. An atom consists of a small nucleus. The nucleus comprises even smaller particles called protons and neutrons. The number of protons present in the nucleus of an atom is known as its atomic number. The total number of neutrons and protons is called atomic weight. Some nuclei are found to be unstable, especially elements with an atomic number of more than 82. To stabilize the nucleus, a few particles leave the nucleus. This process of conversion of radioactive elements into another element by decay is known as transmutation. In fact, a British scientist, Ernst Rutherford, first discovered this process. Rutherford's discovery gave a new direction to modern science. Rutherford was the first scientist who revealed that heavy elements could be converted into lighter elements. In 1908, he was awarded the Nobel Prize in Chemistry for his work. Rutherford found out that radioactive elements emanate radiations, which is in the form of alpha particles, beta particles, and gamma rays. Alpha particles are the nuclei of the atoms of helium that have 2 protons and 2 neutrons. They are of a large mass and move slowly. That is why a thick layer of wind or a strip of paper can obstruct its path. They are positively charged particles. Polonium, with the atomic weight of 214 and atomic number of 84, emits alpha particles and becomes lead. In this way, uranium, with the atomic weight of 238 and atomic number of 92, emits alpha particles and becomes thorium. This emission of helium nuclei is known as decay. Beta particles are negatively charged particles or electrons. In comparison to alpha particles, they move faster. When it emits a beta particle, its movement can be easily obstructed by an aluminium foil. In beta decay, a neutron of a nucleus transforms into a proton and an electron. The electron gets emitted in the form of beta rays and the proton remains in the nucleus. Due to this, the number of neutrons in the nucleus is reduced by 1 and the number of protons are increased by 1. In this way, the atomic weight that is made up of the total number of neutrons and protons remains the same, but the atomic number, which is the number of protons, increases by 1. Like, the atomic weight of thorium is 234 and its atomic number is 90. When it gets converted into protactinium, its atomic number becomes 91. Gamma rays are like the rays of visible light. Neither atomic weight nor atomic number changes by their emission. They have no charge and they are capable of penetrating a very thick material. That is why they are more dangerous. Uranium-235 gets converted into thorium-231, thorium-231 into protactinium-231, protactinium-231 transforms into actinium-227 and then actinium-227 into thorium-227. Thorium-227 gets converted into radium-223, radium-223 into radon, radon into polonium and then polonium into lead-211, lead-211 into bismuth, bismuth into thallium and then it gets converted into lead-207. After getting converted into lead-207, the nucleus of lead becomes stable. Rutherford laid the foundation of nuclear physics by discovering the alpha particles and the new atomic structure. Rutherford refuted the old theory of the inner structure of an atom and developed a new model. Before the model of Rutherford, the prevailing theory about the inner structure of an atom was plum pudding model of J.J. Thomson. Thomson imagined that the positive charge is spread in the whole atom and the electrons are arranged into it like nuts and raisins in a cake. Rutherford's assistants, Hans Geiger and Ernest Marsden, conducted the famous gold foil experiment. They selected a radioactive element that produced a beam of positively charged alpha particles. That beam was then made incident on the round fluorescent screen. The moment the beam of alpha particles collided with the screen began to glow. Now, they placed a thin gold foil in between the beam of the particles. They found that most of the particles passed through the foil undeflected, while a few particles bombarded with the foil also got deflected. Rutherford was surprised to see that a few particles were passing through the foil, while a few got scattered. If he were to observe it according to the model of J.J. Thomson, then positive particles should collide and then get scattered. But a few particles were passing through the foil easily. Then he realized that there is a positive charged heavy core in the center of the atom, due to which a few particles were scattering. Rutherford presented a new model of an atom that had positively charged nucleus in the center of the atom. The nucleus consisted of protons and the electrons were revolving around the nucleus in their orbits, like the planets in a solar system. The discovery of radioactivity introduced a new chapter in the study of physics, which have varied applications in nuclear physics, nuclear medicine, agriculture, industry, energy, food processing, and many other fields. For more than 40 years after the discovery of radioactivity, only natural radioactivity was known. In 1935, the daughter of Marie, Henri Curie, and her husband Frederick Joliot added new discoveries in the history of radioactivity. They made the elements artificially radioactive, which is known as artificial radioactivity. After the discovery of radioactivity, first, it was used in the treatment of serious diseases like cancer. Destroying the cells of cancer through ionizing radiation does the treatment. This therapy is known as radiotherapy. In India, a large number of patients are treated through radiotherapy. Besides this, many diseases are identified with the help of radioactive isotopes. There are many institutes in the country where important research and studies are going on in the field of nuclear medicine. Isotopes emitting less powerful alpha particles are used in the tracers. Radioactive tracers are injected in the body of the patient, and then the condition is diagnosed. Due to the radiations, the functioning of the body parts and blood of the patient can be monitored. Radioactive properties of elements are not only used in identifying the diseases, but also used as an important source of energy, like uranium-235. Apart from it, radioactive elements are being used by archaeologists in determining the age of remains of the ancient period. In the upper atmosphere of the Earth, due to cosmic rays, nitrogen is converted into radioactive carbon-14 isotope, which is absorbed by plants and other living creatures. Throughout the life, its number remains stable due to constant decay and absorbing of C14 isotope. But after death, there is no absorbing and the particles decay continuously. And exactly after 5,730 years, its number reduces to half. And this process goes on and on till the end. The specific time of this decay of particles is known as its half-life. Every element has its own half-life. In this way, at any time, we can count the number of particles present in the dead person and estimate its death period. This is called carbon dating. Through the half-life of carbon-14, we can determine the age of fossils. In this way, on the basis of carbon dating, we are able to calculate the correct age of the Earth and the period of existence of ancient civilizations. It is really surprising to see that a single discovery could lead to so many important possibilities. That discovery will prove so beneficial, even Becquerel might not have thought of it. In fact, radioactivity has generated benefits that extend far beyond the original research, often in completely unexpected ways since its discovery a century ago. Still, there could be many aspects yet to be unfolded. Maybe, in the years to come, some more significant applications of radioactivity will be unveiled. We are not afraid of the alpha ray. A sheet of paper will keep it away. A beta ray needs much more care. Place sheets of metal here and there. And as for the powerful gamma ray, pay careful heed to what we say. Unless you wish to spend weeks in bed, take cover behind thick slabs of lead. Fast neutrons pass through everything. Wax slabs remove their nasty sting. These slow them down, and even a moron knows they can be absorbed by boron. Remember all that we've said, because it's no use remembering when you're dead.